Everyone knows that feeling in a movie theater, right? The explosion that you don't just hear, you physically feel it in your chest.
Oh, yeah, it's a physical force.
But what most of us don't realize is that the huge, maybe 400-pound speaker tower behind the screen is actually split into 4 separate zones.
All just to keep that explosion from completely drowning out a single whisper.
Exactly. And today, that's what we're digging into. We're looking at the QSC SC-444 cinema screen channel loudspeaker system.
It's a really fascinating piece of hardware. I mean, it weighs as much as a motorcycle, but it's engineered with the kind of delicacy you'd expect from a high-end studio monitor.
That's the paradox I really want to unpack. We're talking about a system that costs, what, over $5,000 and weighs 428 pounds? Why does cinema sound need that much mass? Is it just about being loud?
You know, volume is definitely part of it, but the mass is really about control. If you actually look at the architecture here, it's not one big speaker.
Just stack.
It's a modular stack. You have a dedicated mid-high unit sitting on top of 2 enormous low-frequency enclosures.
And the marketing material calls this a 4-way design. I mean, most home systems are 2-way, maybe 3 if you're lucky. Why chop the signal into 4 separate pieces?
It's all about specialization. In a typical speaker, you have drivers that are forced to multitask, covering frequencies they aren't really optimized for.
So they're doing a bit of everything, but not one thing perfectly.
Right. The SC-444 splits the audio into 4 very specific bands. At the very bottom, you've got the low-frequency section. That handles everything from about 35 hertz to 250 hertz.
Okay, so that's the deep rumble. I see here it uses 4 15-inch woofers in total. The spec sheet mentions they are close-coupled. What does that mean? Why does the spacing matter?
That's pure physics. When you pack the woofers really tightly together, closer than the length of the sound waves they're making, the air in front of them starts to move like one giant piston.
Instead of 4 separate fans pushing air.
Exactly. It drastically increases the efficiency and it keeps the sound coverage really wide and even.
Okay, so that handles the physical pressure, the boom. But my issue in theaters is almost never the bass. It's trying to understand what the actors are saying. Why dedicate a whole component just to the mid-range? Can a good woofer and a tweeter handle the voice?
They can, but there's always a catch. In a standard 2-way system, you have what's called a crossover point. It's where the woofer hands the sound off to the tweeter.
And that usually happens around 2 kilohertz, which is right in the middle of the human vocal range.
It is the absolute danger zone for intelligibility. If that handoff isn't perfect, you get phase issues, maybe some distortion, right when an actor is delivering a crucial line.
So you get that muddy dialogue.
Yes. The SC-444 avoids that entirely. It uses a dedicated 10-inch cone driver that operates strictly between 250 hertz and 1800 hertz.
So the entire vocal performance, every word, sits inside this protected pocket of the frequency spectrum. There are no handoffs.
It creates this seamless protected lane just for dialogue. The result is that muddy quality just vanishes because that driver isn't trying to do anything else.
Okay, let's jump to the other extreme then, the really high notes. This system splits the top end into high and very high frequency, or VHF. The VHF driver goes all the way up to 22,000 hertz.
Which, is technically beyond what most adults can even hear.
So why engineer for it? If we can't hear it, what's the point?
It matters because of how drivers behave when they get near their limits. A standard dome tweeter, when you push it hard, suffers from something called dome breakup.
How does that sound like?
It's a harsh kind of metallic sound. The dome literally starts to wobble and resonate in ways it shouldn't, and that really fatigues your ears.
And this system has a way to prevent that.
It does. It uses a specific design called an annular diaphragm. Instead of dome shape, think of it more like a ring.
Oh,
So instead of punching the air like a little fist, it's more like pushing it with a washer. It's just mechanically more stable.
I'm thinking like the difference between pushing water with a coin versus a ring. There's less resistance, less wobbling.
That's a great way to visualize it. Because the ring is supported on both its inner and outer edges, it doesn't warp or break up. It keeps the sound completely transparent, even way up at 22 kilohertz.
So the shimmer of breaking glass or a cymbal crash sounds clean, not like a burst of static.
Exactly. It doesn't turn into white noise.
This is all very impressive engineering, but let's be practical. This is a huge object. 428 pounds is a lot, even for a professional theater install.
It is, but look at its depth. It's only about 20 inches deep.
That's surprisingly shallow.
And that's critical. The space behind a cinema screen is prime real estate. You can't have your speakers pushing the screen into the first row of seats. And that weight has a purpose. It's made of MDF, with very heavy internal bracing.
To stop the cabinet itself from vibrating and making noise.
Absolutely. When you're pumping 1600 watts of power into those low-frequency drivers, a flimsy box would become a secondary instrument. It would rattle and buzz.
You don't want that.
You want the box to be dead inert. The only thing you want moving is the air in front of the drivers.
So the next time I'm in a theater and the sound just feels completely effortless and clear, it's actually because there's a 400-pound machine physically separating the boom from the shimmer to keep them from crashing into each other.
It's a massive, real-time coordination effort happening just out of sight.
Which I think raises a really interesting final question for you to think about. We have these systems, like this one, costing thousands, capable of reproducing sound with near-perfect mechanical precision all the way up to 22,000 hertz. At what point does the complexity of cinema audio engineering actually outpace our own biological ability to even perceive the difference?
Are we building machines for ears we don't actually have?
Something to consider. Thanks for joining us for this deep dive.